Lesson 7.1 is going to incorporate both parts of our preview lesson. We're going to factor with trig terms, and we'll utilize identities when needed to help us in that factoring process. When factoring with trig terms, we're going to apply the same rules as we did yesterday or with 7.0. So it says factor each expression if possible. Secant squared minus 1. Think of secant squared as a perfect square. 1 is also a perfect square. So this is a difference of two squares. And we're able to factor that by splitting apart the secant squared into secant theta and secant theta. We split apart the 1 as a perfect square of just 1 and 1, and we get 1 plus and 1 minus. And that's all you do. Difference of two perfect squares with trig terms. Over on the right, we have cosine squared x minus 4. Again, we've got a perfect square minus another perfect square. What should that look like? We could split apart the cosine squared into cosine x and cosine x. 4 splits apart into 2 and 2. And then you guessed it, we put a plus and a minus in between. And that's factoring with those perfect squares. Sorry, I just had to zoom the screen out so it's easier for me to write. The next one has 3 terms in this quadratic trig expression. Sine squared x minus 3 sine x minus 28. So think of this as our squared term, our bx term, and our constant at the end. Now there's no technical number in front of sine squared except for a 1. What we can do here then is split the c value to get that negative 3 b value in the middle. Factors of negative 28. We could multiply 1 times 28. We could multiply 2 and 14. 3 doesn't go to 28, but 4 and 7 do. In some way, we could get 4 and 7 to equal negative 28 when we multiply and negative 3 when we add by making the 7 negative and keeping that 4 positive. Once we know that pair, and we're not truly splitting the bx term this time, we can go right to our 2 parentheses. We'll break apart that sine squared x into sine x. Oh, I did that before. Not 6, sine x. There we go, sorry. And then another sine x. And we have a 4 and a minus 7. So that 4 just means it's positive. Sine squared x minus 3 sine x minus 28 is equivalent to sine x plus 4 and sine x minus 7. Let's try a cotangent. Cotangent squared x minus 9 cotangent x plus 20. Again, in front of that squared term, we just have a coefficient of 1. So we are just going to go right to that constant at the end, 20. I know 20 has factors of 1 and 20, 2 and 10, 3, no, 4 and 5. If we make both the 4 and the 5 negative, they would multiply to equal positive 20, but also add to get negative 9 as that b value in the middle. Let's see what this looks like. We have cotangent squared x, that splits apart into cotangent x, and another one. And then we have minus 4 and minus 5. And again, you can write those in either order. That's the factored form for cotangent squared x minus 9 cotangent x plus 20. Watch what happens when we have a coefficient in front of our squared term. Here's our 2 cosecant squared x minus 7 cosecant x plus 6. With that 2 out in front, this is the method of a times c split to get b. This gets a little messy with all the trig terms included. I'm going to circle the 2 and the 6 and multiply them. There's your a times c, and that gives us 12. Now, factors of 12, we could do 1 times 12, 2 times 6, and 3 times 4. To get negative 7 in the middle, we'll have to do that negative 3 and negative 4. But this is that process, everybody, where we have to actually split the bx term. So we have to try to fit this all in, sorry. I'm going to do negative 3 cosecant theta minus 4 cosecant theta. And then I'll drop the first term and the last term out in front. 2 cosecant squared theta plus 6. Take a moment if you need to give yourself enough room to write that out. And then press play when you're ready and we'll finish the factor process. All right, once we have these 4 terms, the next step was to put a parenthesis around the first 2 and the second 2. We'll do that grouping method. If we have 2 terms, 2 cosecant squared theta minus 3 cosecant theta, really all they have in common is one of the cosecant theta terms. We'll factor that out to the front. And then to see what's left over, if I had 2 cosecant squared theta in that first blue term, and I factor out just one of the cosecants, I'm going to have 2 and then just cosecant theta left over. And then we do minus. If I take cosecant theta out of 3 cosecant theta, we just have 3 left over. And in that second parenthesis, remember we talked about this before, anytime you've got a negative out in front of your trig term, we have to factor that out. And out of 4 cosecant theta and 6, we can just factor out a 2. This means we have to factor out negative 2. If we take negative 2 out of negative 4 cosecant theta, that would give us positive 2 cosecant theta. And then negative 2 out of positive 6 gives us minus 3. We always know we're in great shape when the parenthesis in this step is the same. So we're almost done, thank goodness. All right, one of our final answer factors is that parenthesis, 2 cosecant theta minus 3. The parts on the outside create that second parenthesis. Cosecant theta and negative 2 become cosecant theta minus 2. And that would be the factored form for that trig expression. It looks like we have a little bit more room on this side, so hopefully you have enough space as well. 4 tangent squared theta plus tangent theta minus 3. Again, with that 4 out in front, we're going to have to do that A times C process. And if we connect them, 4 times negative 3 is negative 12. Numbers that multiply to get negative 12, we can do 1 times 12, 2 times 6, or 3 times 4. Now we want to get the B value, and technically the B value is positive 1. The only way we can do that is by making 3 negative and keeping that 4 positive. That's how we'll split that B term in the middle, that tan theta. I'll do minus 3 tan theta plus 4 tan theta. Again, this gets a little messy. And then we'll take the first term, 4 tan squared theta, put it out in front. And that last term, minus 3, we'll put that at the end. Let's go to the grouping part from here. Put a parenthesis around the first 2 terms and around the second 2 terms. 4 tangent squared theta minus 3 tangent theta, they each have a tangent in common. We can put that out to the front. If we take tangent out of 4 tangent squared, we would just have 4 and a tangent left over. And if we take tangent out of 3 tangent, we just have that 3 left over. Now in that second parenthesis, 4 tangent theta minus 3 is already a match. So we had a problem very similar to this in the 7.0 lesson. If there isn't a specific factor they both have in common, we use a placeholder of 1. And then that would keep 4 tan theta minus 3. And notice our parenthesis matches. That's one factor in our final answer, 4 tan theta minus 3. And then the other parenthesis would get from those outside terms, tan theta and 1 become tan theta plus 1. And there's that factor method. Now the 3 at the bottom would be the ones I would consider maybe either medium or spicy. Let's take a look. Example G, sine x minus the product sine x cosine squared x. In this subtraction problem, it's quadratic because of that squared term. It's actually cubic. You're multiplying 3 trig terms together. But if we look at how it's separated, we've got this first term minus this second bigger term. There really are only 2 terms in this expression. And if you notice, they both have a sign in common. that would be considered a common factor. If we take that out of each term, let's see what's left over. If we take sine x out of itself, there's nothing left over, but again, it needs that placeholder of 1. And if we take sine x out of sine x cosine squared x, we still have cosine squared left over. So we've factored out the common factor. Let's look at the parenthesis now. 1 minus cosine squared. Well, from the very top, 1's a perfect square, and cosine squared is also a perfect square. So like those two problems at the top, this is a difference of two squares, which is factorable. We can split apart the 1 into 1 times 1. We can split apart that cosine squared x into cosine x and cosine x. And then remember the rule in between, 1 is positive and 1 is negative. And then don't forget that common factor of sine x out in front. So in this factored answer, we have 3 separate expressions with those 3 trig terms. And that's the final factored form. And then we run into a problem like this one. Secant squared x plus 3 tan x plus 1. As is with secant squared and tangent, they're not like terms. And when they're not like terms, we can't factor. Which would be great to say not factorable, but we have an identity that can help us. So if we have secant squared and tangent, let's switch that secant squared using our Pythagorean identity. Secant squared x is the same as 1 plus tan squared x. Ooh, I'm going to change that right away. I don't like the double T look that was having. So I'm going to do plus, then I'm going to do tan squared x. If we substitute in that expression, we would have 1 plus tan squared x, and then plus 3 tan x plus 1. From here, I'm just going to kind of combine my constants, and that would be tan squared x plus 3 tan x plus 2. Now this is something that we can factor. Our tan squared term doesn't have a coefficient written out in front, so it defaults to 1, which is nice for us because then we don't have to do the a times c method. We can just split that constant value. And the only way you can factor 2 is 1 times 2. Lucky for us, 1 plus 2 is 3. So this one actually is pretty easy to factor once we recognize which Pythagorean identity is helpful. We can split apart tan squared x into tan x and tan x. And we can split apart the 2 into 1 and 2. And since they're both plus in that factored form on the right, we put plus for both of them. That's utilizing the Pythagorean identity in this factor process. So let's try that again. Look at the expression in its current form. Cosecant squared x minus cotangent x minus 3. Currently, it's not factorable. But again, the Pythagorean relationship comes to the rescue. Cosecant squared can be rewritten as 1 plus cotangent squared. And if we substitute that in place, we get 1 plus cotangent squared x minus plain cotangent x minus 3. Now we need to group our like terms together. I have 1 and minus 3, so that's going to give us cotangent squared x minus cotangent x, and then 1 minus 3 is minus 2. And again, our coefficient in front of our squared term is 1. That means we can go right to that constant, the negative 2. Now the only way we can 2 is 1 times 2, but we have to figure out which number needs to be negative so that when we multiply, we get negative 2, but when we add, we get that negative 1 for the b term in the middle. We would have to make the 2 negative. And then once you do that, split up your cotangent squared into cotangent x and cotangent x. We have 1 and negative 2, which means the 1 has a plus. Wow, let that sink in for a minute. Look at all that factoring with trigonometric terms. This is your lesson for 7.1.